So, have you ever stopped to take a look at a thin, dry layer of paint and the way that it cracks and splinters in really interesting ways? What about the frozen surface of a lake, shattered and broken up into individual polygons? These cracking patterns are pretty common here on Earth. They exist at a wide variety of scales and can be found within a wide variety of materials. However, that's not to say that they only exist on Earth. They also exist across our solar system, on the surface of planets and moons alike. These images are some of the only resources we have to study these distant bodies, since we can't go there. So, how can we take these images and use them to understand the processes occurring on the surfaces here? It's actually simpler than you think. So, there are only two ways in which regular polygons can perfectly tessellate to fill space without creating any gaps. And that is with squares or with hexagons. We can use these geometries to understand the forces at play that are creating these patterns. When we see squares, we understand it to mean that there's been some sort of compression or squeezing of the material. And when we see hexagons, we know that there's been some sort of tension or pulling on the material. Now you may be thinking, well, we don't see a lot of perfect squares and perfect hexagons in real life. Right. How then can we say that these are regular polygons? Well, it turns out that the cracks created by these fracture networks form what can be very well approximated as regular polygons. So much so that their shape can be quantified with just two variables, nodal degree, or n, which is a measure of the number of corners for a given junction in our network, and vertex degree, or v, which is a measure of the number of corners in a given cell. For example, a T-shaped junction has nodal degree equal to 2 because there are two corners that meet at that junction. And a square has a vertex degree of 4 because it has 4 corners. So P here is a ratio of the number of T-shaped junctions, or n equals 2, to the total number of junctions, and this gives us a feel for how regular the network is. We can apply this framework to these fracture network patterns we see on other planets to better understand how these patterns were formed, as well as potentially how many times they've been broken without ever setting foot on these distant surfaces. Now I'm going to take you on a brief tour of our solar system through the lens of these cracked patterns to better understand how truly ubiquitous they are. We're going to start here on Venus. Here is one of the networks that we isolated on Venus. If we take a look at our plot on the left-hand side, on our x-axis, we have the nodal degree, which again is the number of corners per junction in the network. And on the y-axis, we have our vertex degree, which again is the number of corners per cell. These two values are averaged over the entire network and plotted as a pair. Up here at the top, we have our regular hexagons, and along this line at the center, we have our regular squares. And here is where this particular network plots in relation to our regular polygons. Now let's take a look at Mars. Here's the fracture network that we isolated on Mars. And here is where that network plots in relation to our regular polygons. Now, let's look at Europa. Europa is a moon of Jupiter. And as you can see just from the surface alone, it is highly broken up. When you zoom in, here is the network we took a look at, and here is where it plots in relation to our regular polygons. Now, last but not least, poor little Pluto, all the way out on the edge of the solar system, no longer a planet, but still very important for our understanding of these cracks. So, here is one of the surfaces we looked at on Pluto, and here is where Pluto plots in relation to our regular polygons. Now, you may be thinking, if these are well approximated as regular polygons, why don't they plot where our regular polygons are? Well, that has to do with trajectories. So, as you can imagine, once these fractures form, they're not going to stay that way forever. It's likely that they'll be broken again and again, and as these changes occur to this network, we can track changes in the nodal degree and vertex degree, n and v, with each successive breaking or changing of the network. Work done by Goering et al. In 2014 shows us that when you have a square network and you repeatedly wet it and dry it, on average you will tend towards a hexagonal pattern with each repeated wetting and drying, following along this yellow arrow here. Work done by Demokos et al. In 2020 shows us that an existing pattern of crisscrossing fractures, when you break the cells up and you break them in half, you drive the system along this green trajectory here, which starts out as a kind of graph paper pattern, will eventually become a more brick-shaped pattern with repeated breaking. Now, let's go back to our planetary data. So, as you can see, we have kind of three patterns that set the bounds on our plot. Over here on the left-hand side, we have our regular squares that form brick-shaped patterns. At the top, we have our regular hexagons, which are kind of akin to honeycomb. And over on the right, we have our grid-shaped pattern of regular squares. Now, as you can probably tell, the majority of these planetary surfaces are plotting very close to this brick pattern, as opposed to our hexagons or graph paper pattern. Now, why is that? Well, the absence of graph paper pattern has to do with the trajectories mentioned prior. So with the repeated breaking in half of these initial grid-shaped patterns, you're driving the system to look more and more like bricks with each repeated instance of breaking. You can imagine that as these cracks sit exposed on the surface for longer periods of time, you're going to end up with more brick-shaped patterns on average than grid-shaped patterns. Now, what about the honeycomb pattern? Where is it? Well, this is Giant's Causeway in Ireland. Now, you would be very hard-pressed to find cracks like this in the Wissahickon. Why? Well, this required conditions to form these particular networks are very, very specific, and any small deviation from the required conditions will cause a totally different shape to form. If you were to quantify all of the fracture networks that we have here on Earth and create a pie chart, there would be a very small sliver that would make up networks like this one. Now, imagine taking that and extrapolating out to the solar system. A problem emerges. Finding these hexagons is like finding a needle in a haystack. However, that's not to say that there's no needle. And as we continue to comb the solar system for more of these fractures, we plan to populate this graph on our ever-shifting journey of understanding worlds beyond our own. Thank you.